This video was produced in order to show you each of the actual control results of installing a pneumatic control valve and an electric control valve in an actual flow control loop. Please take a look. Presently, pneumatic control valves are still widely used in plants, not only in Japan, but also all over the world. This may be the result of their long history of automation and the technical challenge to create electric valve actuators with better control performance than pneumatic types. Recent major advances in magnetic materials have enabled the development of stepping motors that provide powerful operation just by applying a pulsed current. They have made ideal control performance attainable. STEPTOP is a series of stepping motor-driven electric valve actuators perfected by M-System. This is the structure of a linear motion type STEPTOP. The stepping motor is mounted in this area. A stepping motor's rotary motion is converted to linear motion via a reduction gear mechanism by means of a screw nut composed of a screw shaft and a nut. By using STEPTOP, this resulted in an electrically operated control valve with a smooth movement, resolution well in excess of 1/1000th, no overshoot movement, and no effects of the reaction force of fluid pressure. And now, various types of electric control valves with STEPTOP are widely used in various industries. Electric control valves with STEPTOP do not need any of the incidental air supply equipment that is a mandatory requirement for pneumatic control valves, including compressors, air dryers, air lines, pressure-reducing valves, and filters. The control operation begins immediately just by connecting a power supply and applying a signal of 4 to 20 milliamps. As a result, the cost of the equipment, including the control valve itself, is 1/5 of that of the pneumatic type, and the energy consumption is 1/10. In addition, the electric type does not require complicated maintenance work like the pneumatic type. A simulated plant facility named Plantlet is installed at the headquarters of M-System. The Plantlet is a full-scale mini-plant for practical training, equipped with machinery and instrumentation systems equivalent to those of a real plant. By using the pneumatic control valve and electric control valve installed in the Plantlet, you will now see a comparison of their performance in a flow control loop. This is a flow diagram of the Plantlet. In the Plantlet, the water in the tank is circulated by a pump, and the system is capable of controlling the flow, the water level in the tank, and the temperature. Let's focus on the flow control loop in the flow diagram. This is the circulation pump. The discharge rate is 70 liters per minute. This is the electromagnetic flow meter that measures the flow. The measuring range is 0 to 40 liters per minute. The electric control valve and the pneumatic control valve are installed in series on the same piping for flow control of the circulation line. One of these two control valves can be used by switching it with a single switch, and the other control valve not in use will be fully opened. This is the pneumatic control valve. The control valve is a 25A globe valve. This part is the diaphragm motor, pneumatic positioner, and pressure-reducing valve with filter. The IP transducer is installed here. The pressure-reducing valve with filter is also attached here. On the other hand, this is an electric control valve. The STEPTOP MSP5 is mounted on a globe valve with the same specifications as the pneumatic control valve. As you can see, it is a very simple configuration. Here, cutaway control valves are used to compare the operation of the pneumatic control valve and the control valve with STEPTOP electric actuator. On the left is the pneumatic control valve, and on the right is the electric control valve. The position control signal of each control valve is changed in a stepwise manner from 101.5% to negative 1.5%, and then to 101.5%. First is the pneumatic control valve. It went from fully open to fully closed with fast response. It is now full open. The operating time for complete travel is about 0.5 seconds in both directions. Next is the control valve with STEPTOP electric actuator. It starts to close. The valve changed from full open to full close. It starts to open. It is now full open. The operating time for complete travel is about 6 seconds in both directions. Check the trend graph of the recorder to see the movement in both directions. The position control input common to both is depicted in red. The position output of the pneumatic control valve is depicted in green. And the position output of the control valve with STEPTOP electric actuator is depicted in blue. As you can see, the position of the pneumatic control valve responds in a first-order lag with a short time constant, while the position of the control valve with STEPTOP electric actuator responds with a ramp-like constant speed. As you can see, there's a big difference between the operating characteristics of the two control valves when you look at the valves by themselves. Then, what kind of difference in control characteristics will occur when used in an actual control loop? Let's compare the response characteristics of a control loop between a pneumatic control valve and a control valve with STEPTOP electric actuator using Plantlet's flow control loop. First, select the pneumatic control valve with the control valve selector. This is the single loop controller SC series used for the flow control loop. It uses a full dot LCD screen with touch panel to display and to operate. In this video, the SC series will be referred to as the PID controller from here on. Make sure that the control mode of the PID controller is set to manual and start the pump. Water begins to flow, and the indicated value of the electromagnetic flow meter has increased. Set the control mode to auto. Take a look at the tuning screen of the PID controller. The proportional band PB of the PID controller is set to 73%. The integral time, TI, is set to 0.13 minutes, and the derivative time, TD, is set to 0 minutes with no derivative operation. These are the optimal parameters according to the Ziegler-Nichols open loop method. After the loop is stabilized, let's change the flow set point value SP in a stepwise manner and see the response characteristics of the flow process value PV and the control manipulating value MV of the PID controller. Switch the screen of the PID controller to show the digital display screen. Touch SP to bring up the numeric keypad window, enter 10.0 liters per minute, and press Enter key. Switch the screen of the PID controller to the short trend display, and you can see the response of the control loop in a trend graph. The flow process value PV is depicted in green, the set point value SP in red, and the control manipulating value MV of the PID controller in blue. Next, let's look at the step response characteristics of the control loop when the control valve with STEPTOP electric actuator is selected. Switch from a pneumatic control valve to an electric control valve. Take a look at the tuning screen of the PID controller. The proportional band PB of the PID controller is set to 60%. The integral time, TI, is set to 0.13 minutes, and the derivative time, TD, is set to 0 minutes with no derivative operation. These are the optimal parameters according to the Ziegler-Nichols open-loop method. The values are different from those of the pneumatic control valve. Let's see the response characteristics of the control loop by changing the set point value SP in a stepwise manner in the same way as for the pneumatic control valve. Switch to the short trend display screen of the PID controller. As in the case of a pneumatic control valve, the response of the control loop can be checked in a trend graph. The position output of the electric control valve is added to the trend graph as a light blue trajectory. Since we have recorded the data of the PID controller on a computer, we will now check the recorded data by viewing the screen created on a computer. The upper half of the screen shows a trend graph when using a pneumatic control valve, and the lower half of the screen shows a trend graph when using a control valve with STEPTOP electric actuator. To the right of each, the present value of trend graph is digitally displayed. The flow process value PV is green. The set point value SP is red, and the control manipulating value MV of the PID controller is blue. The position output of the control valve with STEPTOP electric actuator is light blue. Since the current values of PV and SP are the same at 5 liters per minute, the trend graphs overlap. Since the current values of MV and the position output are also the same, the trend graphs also overlap. In addition, an image of water flowing from the control valve into the tank is placed on the left side of each of them, allowing you to see the change in flow in the form of water flow. Let's take a look at their response characteristics while running them both simultaneously by aligning the time axis at the top and bottom of the screen. Change the SP from 5 liters per minute to 10 liters per minute in a stepwise manner. The control operation of the PID controller immediately increases the MV and activates the control valve, resulting in the PV starting to follow towards the SP. Since the position output of the electric control valve matches the MV, we can see the trend graph overlapping. The PV has stabilized in line with the SP. We can see that about 40 seconds have passed. In the movement up to this point, The response characteristics of the pneumatic control valve and the control valve with STEPTOP electric actuator are equivalent. Next, we will change the SP in a stepwise manner from 10 liters per minute to 15 liters per minute. To shorten the viewing time, we will fast forward at 4 times the speed. After about 40 seconds, the PV matched and stabilized. Change the SP from 15 liters per minute to 20 liters per minute. As before, the PV matched and stabilized. Change the SP from 20 liters per minute to 25 liters per minute. It changed with the same pattern as before. Now, we will return to the original speed. Now, we will change SP drastically from 25 liters per minute to 5 liters per minute. Since the deviation between SP and PV is large at first, the control manipulating value MV of the PID controller also decreases rapidly. The position output of the electric control valve keeps up with the rapid changes in MV without delay and matches it. It took about 55 seconds for the PV to match and stabilize. Now we reverse the process and change the SP drastically from 5 to 25 liters per minute. The MV increases rapidly. Again, the position output of the electric control valve follows the changes in MV and matches it. The response of the PV is equivalent for the pneumatic and electric control valves. It still took about 55 seconds for the PV to match and stabilize. This is the same time as for the downward direction. Finally, the SP is lowered from 25 liters per minute at a rate of 5 liters per minute. The PV responds and follows the SP. The position output of the electric control valve matches MV. It took about 40 seconds for the PV to match and stabilize. This is the same time as in the upward direction. From here on, we will fast forward at 4 times the speed. The SP was changed from 20 liters per minute to 15 liters per minute. PV responded, matched, and stabilized. Changed SP from 15 liters per minute to 10 liters per minute. PV responded, matched, and stabilized. Changed SP from 10 liters per minute to 5 liters per minute. PV responded, matched, and stabilized. We have now confirmed the response characteristics of the flow control loop using a pneumatic control valve and an electric control valve equipped with a STEPTOP. In both cases, we can say that the step response characteristics are typical for a general flow control loop. Now, let's compare the step response characteristics of the two in the trend graph. The flow process value PV is green, the set point value SP is red, and the control manipulating value MV of the PID controller is blue. The position output of the control valve with STEPTOP electric actuator is light blue. As you can see, the response trajectory of the PV to the change in SP is indistinguishably the same throughout the entire flow range. The time required for the PV to match and stabilize was about 40 seconds for both the 5-liter per minute change and about 55 seconds for both the 20-liter per minute change. There is no noticeable difference in the movements of the MVs. In addition, since the STEPTOP follows the movement of the MV with a resolution of more than 1/1000th, we can see that the trend graphs of the MV and the position output of the electric control valve overlap over the entire area. From this result, we can confirm that the step response characteristics of both are equivalent. As you have seen earlier, the standalone operating characteristics of the pneumatic control valve and the control valve with STEPTOP electric actuator differ greatly. On the other hand, since the response characteristics of the control loop are determined by the characteristics of the entire loop consisting of sensors, PID controllers, control valves, and processes, it was found that the difference in the operating characteristics of the control valve alone does not affect the entire loop. In this study, the results were the same even when comparing the flow control loop and a fast response speed. Therefore, there will not be a difference in the response characteristics between the two for control loops with response speeds slower than the flow, such as temperature and liquid level control loops. As an example of the response speed of the liquid level control loop, here's a trend graph of the plantlet's tank level control loop when the set point value is changed in steps. Again, a control valve with STEPTOP electric actuator is used here. The tank capacity of the plantlet is about 0.15 cubic meters, and the minimum water residence time when full is less than 4 minutes. It takes about 6 minutes for the water level PV to stabilize in line with the set point value SP, which is a slower response compared to the flow control loop. The above comparison demonstration shows that when the control valve with STEPTOP electric actuator is used in an actual control loop, the control result is comparable to that of a pneumatic control valve with positioner. In addition, as mentioned earlier, the STEPTOP has the great advantage of being compact, requiring no air supply equipment and significantly reducing equipment costs and energy consumption. The era of control valves with STEPTOP electric actuator has finally arrived. If you are using a pneumatic control valve, please adopt this product. M-System issues a collaboration catalog with valve manufacturers who have agreed. If you would like to know more details, please contact M-System. Thank you very much.